All right, so we are moving into chapter 16. We're going to be playing with pH for a while now. This was covered in physical science. If you got to it, I'm not sure if you did or not when you guys took it, but it is something that I'm sure, or I should say, something that you have heard discussed in common speech. People talk about acids and bases and pH balance, and so we're going to get into the science of it today. I bet a lot of this you already know. You did some work with the first part of this chapter yesterday, defining the different views of acids and bases. So we're going to look at the pH scale and how we measure acidity today. I'll give you just a second to write that down. So pH scale. Scale isn't something you measure against. The pH scale goes from 1 to 14. It's a logarithmic scale, so the difference between 1 and 2 is not the same as the difference between 2 and 3. It's the size of the scale gets bigger as it goes up. It's a logarithmic scale. It's actually powers of 10. So the difference between 1 and 2 is between 1 power of 10 and 2 powers of 10. That's from 10 to 100. But then from 2 to 3, that's from the second to the third power of 10. So you're going from 100 to 1,000, right? So the logarithmic scale is actually taking the exponents of powers of 10 and making them the number. So like 1.5 is 10 raised to the 1.5 power. A pH of 7 is 10 raised to the 7th power. Okay, so it's a logarithmic scale. You have all been exposed to logarithms by now in math, and so that's the kind of scale that this is. The closer a pH value is to 1, the stronger the acid that it is. A pH of 1 is very, very, very strong acid. Okay, and then the closer the pH value is to 14, the stronger the base. And then a 7, of course, lies right in the middle, and a pH of 7 is a neutral substance. So distilled water is a pH of 7. Your blood is slightly acidic. It's not 7, it's just a little below that. Some things are only slightly basic. They would be like this pH of 7.5 or 7.6. But if you see pHs of 4 and 5 or 2 and 3, those are acids. pHs of 8, 9, 10, that's in the basic side. Yes, sir.
I was just going to ask you because you ever tasted blood before it's bitter, right? So wouldn't that mean it's base?
Oh, you know what? You're right. I thought it was slightly acidic, but it's, never mind. It's slightly basic. You're correct. So common things on the pH scale. Hydrochloric acid, stomach acid is right around 0. It's about as strong as acids can be. Juice of a lemon, pH of right around 2. And then vinegar is just under 3. An apple is 3 points small, 3.3 or something like that. Tomato, right around 4. A banana is 4 point large, 4.7, 4.8. Milk is pretty much neutral, but it is ever so slightly acidic, 6.6, 6.7. Distilled water is the definition of neutral. So they set pH meters with distilled water and tell it this is 0. Or sorry, not 0, this is 7. This is right in the middle neutral. Blood is slightly basic, 7.5-ish. Baking soda, more basic, 8.5-ish. Soap, pretty darn basic, 10. Ammonia that we use for cleaning, 11.5. And then drain cleaner is pH 14. We tend to use bases as cleaners because they break apart fat molecules pretty well. And a lot of greases, and the reason dirt sticks to things is because of fat molecules. So bases tend to break those apart pretty well. We tend to use acids to simplify other kinds of molecules. Acids tend to get into molecules and break bonds pretty well. especially metal bonds. Metals and acids react famously. But foods tend to be acidic, and your stomach acid is more acidic breaks these things down. Okay, which is why drinking a glass of milk, which is nearly neutral, 6.5, if you have heartburn, stomach acid in your esophagus, milk will react with that and will help bring the pH back up towards neutral. It won't totally neutralize it, which will wind up with pHs around 5, which is a lot easier to have in your esophagus than pHs of 0. So you can see some common things on the pH scale. The pOH scale is the same exact concept, but the polarity is switched. We don't use pOH nearly as much as we use pH, but you should be aware of it. Okay, so 1 is a strong base and 14 is a strong acid. You're going to use pH a lot more than you will use pOH. So if you want to just remember that pOH switches things, right? So acids are normally low, and pH and bases are very high. And so pH and pOH scales are calculated based on what a substance does to water when it goes into solution. I'll show you examples of that. The pH measures the concentration of hydrogen ions produced, which winds up being hydronium H3O instead of H2O. And the pOH concentration is the pOH scale measures the concentration of hydroxide ions. So when an acid or a base goes into water, it will either free up hydrogen ions or it'll create hydroxide ions. And we can measure the concentration of those things and determine the pH of it. Okay, so pH measures what it does to the water, not the substance itself, which is why I can have dry acid powder, and if I were to try to measure the pH of my dry acid powder, there's no reading that I would get. But then when I take my dry acid powder and put it in water and stir it and let the powder dissolve in the water, then I can get a pH reading, because I'm measuring what did that acid powder do to the water. I'm actually measuring the water's response, not the powder itself. Okay, so this shows you here, when I take hydrochloric acid, a dry acid powder, and I combine it with water, the hydrogen from the hydrochloric acid winds up bonding to a water molecule and forming hydronium, H3O. And then the chlorine floats around by itself. It dissociates, and I have aqueous dissolved chlorine and hydronium. And my pH meter is going to actually look for the amount of hydronium and tell me the pH of the water. So I'm not measuring this at all. I'm measuring what it did to water. Okay? So this is just another picture of that. If I have a strong acid, like hydrochloric acid, I combine it with water. One of the hydrogen from the hydrochloric acid winds up joining to water, and I get this hydronium ion plus a chlorine ion dissolved in the water. And this is what I'm measuring on a pH scale. A base, the exact opposite, right? I take a strong base like sodium hydroxide, and I add it to the water, and it's going to dissociate in the water to sodium ions and hydroxide ions. So here I have hydroxide ions and sodium ions in the water, and this is what my pH scale is going to be looking for, this excess hydroxide ion in the water. Okay. A substance's pH plus its pOH equals 14. So this is just a way of converting between pOH and pH scale. If you have a pH of 2, you don't need to do any fancy math to figure out the pOH of that thing. pH plus pOH equals 14. So if you have a pH of 2, you have a pOH of 10. Pretty simple. If you have a pH of 7, you also have a pOH of 7. You just need to figure out what you have to add to that thing to make it 14. So a pH of 2 and a pOH of 12 is the same meaning because they are opposites of each other. One measures one aspect of the water, the other one measures the other aspect of the water. pH or pOH is the negative log of the ion's molarity. So this is where we're going to get into some math. So in order to calculate the pH of a solution, you need to know the molarity of hydrogen ions or the molarity of hydroxide ions in solution. And then when you express the molarity, you get you're looking for the exponent there, right? And it's the negative log. So if the concentration of hydrogen ions in solution is 1 times 10 to the negative 6th molar, all you're doing is lifting this number out of the expression. And that is the pH. But it's the negative log of that. So it's not negative 6. You never have a negative pH. It's just the 6. So expressing this in math, the pH equals the negative log of 1 times 10 to the negative 6. The log of 1 times 10 to the negative 6 is negative 6. So it's the negative 6, which is just 6. If this confuses you, all you have to do is see the number here. Ignore the negative sign, and that is your answer. Okay? So the concentration of something is 1 times 10 to the something. That number is your pH. Okay? This operation can go backwards. So if you know the pH or the pOH, you can calculate the molarity. If the pH is 9, what's the molarity? Well, the hydrogen ion would be 1 times 10 to the negative pH. So 1 times 10 to the negative 9th molar. So the pH again is just the power of 10, but it's the negative power of 10. If pH is 9, the answer is 10 to the negative 9. And it should say 1 times 10 to the negative. Okay, so pH is just the exponent. pH is just the exponent. But it's the exponent when it's expressed as 1 times 10 to the something. If you wind up with the molarity of 6 times 10 to the negative 4th, the answer is not 4. You've got to manipulate your exponent so that it's 1 times 10 to the something. Okay, and we'll do some examples showing you how to do that. I'll leave this up here for a second because it's so some substances, they're called amphoteric substances, can either serve as a base or as an acid. Remember from your activity yesterday, there are different ways of defining an acid or a base. If something is able to give away a proton, then it's an acid. If something is able to receive a proton, then it's a base, right? There are some substances that, depending on what situation it's in, can either give away a proton or receive a proton, depending on what you mix it with. And those things are called amphoteric substances or amphoteric compounds. It can play the part of an acid, or it can play the part of a base, depending on what it's mixed with. Generally, amphoteric substances play a base if they're with an acid, or play acid if they're with a base. So they're able to play either role depending on what you put them in a reaction with. But generally speaking, amphoteric compounds are not able to be a strong acid and a strong base. They tend to be either a better acid or a better base. So we could make this a sports analogy, right? When I was on the swim team, I was a sprinter. I didn't have the endurance to be fast for a long time. but I could be really fast over short distances. So I was good at the like 50 meters or 100 meters, and then when it got longer than 100 meters, I started to not win races, right? But I was really good in a short throw. So if you put me in a race against people who were not as fast as I was, I could play sprinter, and I was a good sprinter, and I could win in the short races. But when I had to go long distances, if I were put in a 200-meter race, I can do it, but I'm not as good at it, right? So there's a comfort zone where I'm better here, but I can do this if I need to. There are some compounds like that where they're comfortable, they're a good acid. But if they're put in the context of an even stronger acid, they can be an okay base. Okay, and so an amphoteric compound is either a good at one thing and okay at another, or good at the other and okay at this one. Very rarely do you see an amphoteric compound that is both a really good acid and a really good base. Okay, and then there is something called a polyprotic acid. And these are acids that have more than one proton to give up. Hydrochloric acid, one hydrogen, and a chlorine ion. So it can only give up one hydrogen ion to solution. But sulfuric acid is able to give up 2 protons to solution. So one molecule of H2S that goes into water actually does twice as much to lower the pH as one molecule of hydrochloric acid. So one molecule of hydrochloric acid can only add 1 proton to the solution. One molecule of sulfuric acid can add 2 protons to the solution. So it lowers the pH twice as fast. H3PO4, this acid can actually give 3 protons to solution. So one molecule can lower the pH 3 times as fast. Okay, so polyprotic acids tend to be very strong, and they tend to increase the acidity of solution rapidly because they have more protons to give away, to donate to the solution. Okay, so these are some concepts that you will come across. How do we measure pH? pH can be measured a couple of different ways. With color shifting indicators, and there's a lot of them. This is what we'll be doing with our lab this week, is playing with color shifting indicators and watching a compound which is able to indicate the presence of a solution above or below a certain point of acidity or basicity. We'll watch these chemicals change color, and then we'll be able to see where the pH is. The other one is with a probe, an electrical conductivity device. And the probe measures the conductivity of the solution and compares it to a reference. pH probes are more accurate, but they're very expensive, and they're kind of hard to use. We don't actually own any pH probes. They're just not cost effective for the number of times that we would use them in class. But when you go to college, they will probably own them, and you'll probably get to play with them in a college chem class if you wind up taking that. But what these things do is you tell the computer that's associated with them that this conductivity is 7, distilled water. Then you take the probe and you put it in your solution, and the more ions, the more hydrogen or chlorine or whatever kind of ions that it encounters will affect the conductivity of that solution, and it'll say, oh, this is more conductive or less conductive than what I was just in, and it'll be able to read pH that way. Those are much more accurate, but they're hard to use. Color shifting indicators are very, very cheap and very easy to use, and so that tends to be much more common. Litmus paper, based on different kinds of compounds, will usually only have two colors. Pink might turn blue, blue might turn pink. But then there are papers that have lots of different chemicals in them, and they all change colors differently based on the pH that it's in, and so the resulting color you can read against a scale. And so, is it tomorrow? I think it's tomorrow. Maybe it's Thursday. You'll be using universal indicator, and you'll be able to read the color of the paper against a color scale, and it will tell you what pH you have. You can also use natural sources. A lot of dark red natural juices like cabbage juice, cherry juice, grape juice, they will turn color as well in different pH solutions. And so you can use natural juices to help pH. And you'll do a little bit of that with the lab as well. Okay? We'll be doing this kind of stuff for a while. This is a probe. We don't have any Hello probe. And they're, like I said, they're fairly complicated to use, but they're very accurate. You get readings like 7.24 for your pH. But if you compare that to these kinds of scales, you'll never be able to read this and say 7.24 because you're comparing color scales. You might say, well, it's a little more blue than that, but you won't know. You won't be able to say 7.24. Whereas on a digital scale, you would be able to get a very exact reading. Okay, that is it. What questions?